year ago today, the first COVID case was actually.
Nobody asked Aiden.
That true?
Yeah.
Wow.
The first COVID case popped up in China.
Huh.
Happy birthday, Kobe.
Was that like when COVID started, or like after that it then became a thing? I don't remember the timeline.
We're in the Midwest.
Oh no, that makes sense. That makes sense. Yeah.
We're in the Midwest, right?
Yeah, because then.
Okay, because 97% of Midwestern countries. Okay, that's countries, my bad. But,
So then, yeah, short. Like it was April when it got real bad.
yeah. There you
Okay, that makes sense.
97%.
That timeline. Okay. So guys, I'm back. Sorry that I was gone. It was not my choice. So, like that Monday that I was here, the day before we'd had a friend over for dinner, who then told me when I got home from work Monday, oh, by the way, I just got tested positive for COVID. So I was like, super. So I called the nurse, Miss Yako, and was like, hey, this happened. She's like, oh, you're home for 2 weeks. I was like, oh, okay, thanks, bye. I mean, that was the end of the story. Got my test. It was negative, so my wife and I were both negative. So, but she had to quarantine from school. She's a student at IWU. So we were both stuck at home. She loved it because she never gets to see me. So we got to I enjoyed it too. I was working the whole time, and she was just trying to like talk to me and hang out. I was like, hon, I gotta work. This isn't a vacation. So it was good. It was nice to be home with her. It was weird. It was hard to like teach virtually. It was hard to switch all my classes to be on classroom, right away. Like that Tuesday was like, I was up till like 10 o'clock trying to get stuff ready. And then it was hard to keep stuff going. So anyway, that was my time. It was some good things, but it made it kind of hard. A lot of my classes, you guys I think did okay. A lot of my other classes, kids were just not doing anything. They just assumed because I'm not here, they don't have to do anything, even though it was all being posted. So that's been a nightmare to try and catch up with. You guys, I want to get some feedback. And to be honest with me, like, how did the last 2 weeks go? Okay, good. From my end, I thought it was also okay. So you guys notice I was posting those AP videos. Give me a thumbs up, okay, or like give me some feedback of how helpful those were. Like, I need everybody, just give me some feedback. So?
Yeah.
Andre?
So.
Okay. To me, I really like them because, one, it's straight from AP. It's also straight to the like key concepts and skills that you're going to be tested on for the test. I really want to hang this up. Any ideas of where I could hang this up? This is like the blueprint for this class. That's right. So we're in Unit 4, Energy, which is one of my favorite units, by the way.
You see, when you show it like that, it doesn't look like that much.
It's
like
not.
There's only like, that one has 2, 3.
Yeah.
Unit 3 had the most.
Yes, Unit 3. However, Unit 3, 4 to 6% of the AP test.
What?
Why?
Yeah.
What?
So this is something that's really tricky. All these units might be equal in terms of time taught in the classroom, but the amount of questions from each unit aren't actually like split evenly. Look at this unit right here, Unit 4, 16 to 24% of your AP test will be questions about energy. So potentially a quarter of your test will be on Unit 4, right? So that's another thing. We're going to look into this more kind of at break, and then once we are really preparing for the test, to strategize. Don't spend all of your time studying Unit 3 if it's only 5% of your test, right? That's going to be something that you need to consider. Everything important. Everything is going to be on the test somewhere. It's just some things are going to be really important. But we're going to look at this later. But I also wanted to show you what was I gonna say? Someone asked.
Talking too
What?
early.
What?
Where are we putting it up at?
Oh yeah, where do you want me to put this up? Oh, the AP videos. Those
Right.
videos are directly related to these skills. The skills that you need to know for the test. Those videos, if you notice, it's like, investigate an open and closed system. That's like a skill that you need to know for the AP test. That's another reason I really like the AP videos, because they make them specifically for these skills. So I'm going to continue to use them. Sometimes we'll watch them together. Other times I'll assign it as homework. Like, okay, watch these 2 videos to review this topic or introduce next class's topic. But I'm glad that you guys also had an overall positive view of the videos and found them helpful. Because I'll continue to do those. They're a really good resource. That also helped me a lot because I couldn't be here in person to teach. And so those videos kind of took place of introducing topics for me. Yeah, I don't know, can I put it here? Is that a stupid place to put this? Huh? Up there? Yeah, that's true. Is it visible if I hold it up like that?
Yeah.
Okay, I can do that. I'll have to.
I mean, you can't read 100% of the little.
True. But at least you can kind of come look and check in. That's something I've been wanting to put up and to make you guys aware. Again, for this semester, we're still on track. We're going to finish Unit 4. I think we'll test next week. So right before you go to break, we're going to test on Unit 4, end Unit 4. And then when we come back, we'll have 3 weeks to get through Unit 5, test right before Thanksgiving or Christmas break. And we should have an extra day that we can kind of hang out, kind of talk about the AP test, just kind of think.
Physics related movie.
Yes, that we could, if we get that free day, depending on how things go, that could work. Can you guys give me other feedback of how the last 2 weeks went while I was stuck on quarantine? Was the content making sense? Were we okay? Or yeah, I'm on track, I get it. Or no, I don't understand it. Or no, this topic, I don't know what this is. Give me some feedback. Help me figure out where we're at.
The Fit Lab wasn't too bad.
Okay?
Because for the most part, it was just pretty straightforward. You just follow along.
Good.
Except for one hiccup when you asked for the speed, and you said click the I can't remember what it's called.
Speedometer, but
The
it didn't have
speedometer.
any numbers on it.
Yeah, it didn't have any numbers at all.
Oh.
Yeah, but
Well,
So I literally
like
spent
5, 10, 15, 20.
I think that was more looking at this situation. It's really fast. This situation, it's not so fast.
Wait, so I literally answered not fast, medium fast, and fast. Was I literally correct?
Yeah, it's a relative. So I guess you didn't.
Guesstimate. You put 25 or something like that.
Yeah, that's
I'd rather
fine.
notch a 5,
Yeah,
10.
that's a good way to interpret. Yeah, it wasn't what mile per hour was it? It was more. I can't remember the exact scenario, but if you start up high, the speed gets really fast. If you start kind of high, the speed doesn't get as high. It was more compare the two rather than what was the speed. So that wasn't super clear, but I think you guys all figured that one out.
Yeah, I was just telling you that happened.
Okay, appreciate that. Good, the energy lab was important, right? It's really important to look at the system as a whole and look at total energy. The skateboarder started up top with no velocity. All the energy in that system is potential. When you let him go, that potential energy switches and gives the skateboarder motion. That's now kinetic energy, right? What happened when you got to the very bottom? What happened to your potential energy when you hit the bottom of the skate park? It was gone, right? You aren't off the ground anymore. You don't have any potential energy. What happened to that potential energy? Where did it go? Kinetic energy. It didn't leave the system disappear. It got converted from one form of energy to another. What happened when the skateboarder continued back up the ramp? Speed decreased. Huh? Yeah, because you're going up away from the ground now. The further away from the ground, the more potential energy you get. What happened at the very top? Bingo! You run out of kinetic energy, you stop moving. You're temporarily paused, maximum potential energy, and then what happens?
Go right back down.
You go back the other way. You got a bunch of potential energy. Well, that gets converted to kinetic energy, and it goes the other way. And it goes back and forth. That's your system. So the total energy stayed the same, didn't it? If you paused it at any point, the what?
There's no energy added or taken away.
Bingo. So what kind of a system was that? Okay, right? Open, closed, or then isolated. Those are the three types of systems. That was a closed system. Was isolated, no mass transfer?
No energy.
No energy at all?
Yeah.
Okay.
Well, like you can't.
I honestly don't remember. Those two are very similar. And I can't remember the specific difference off the top of my head, to be honest with you.
System, energy and matter cannot enter or leave the system.
Isolated?
Well, that one's not a
Okay, yeah. Open system is you could have energy go in or out and matter go in or out. A closed system, you can only have energy. So your energy, you could lose energy, but whatever objects are in your system are stuck there. Isolated means nothing goes in or out. Right? So that was another good one. That's great. That's a good summary, that lab, because it talks about all those pieces. Any other feedback that you got for me to do?
I think I still have to pull it up, but there was one of the question things that I didn't really understand well. Like I didn't know how to answer the question, and since you weren't there, I couldn't really just ask.
Fair. Was it like one of the homeworks on myAP? Yeah, I
It wasn't
think
on my AP.
I want to remind you guys that a lot of you haven't done the homework that I assigned to myAP. There's a 4.1 that is like 6 questions, all about 4.1. 4.2 was 10
It
something.
was like
16, it was a little more. That was all about 4.2 subjects. 4.2 is a lot bigger unit.
When did we get that?
That I assigned
That was
Friday. Yeah, Friday, that was my homework, is on my AP classroom, I had assigned like a 4.1. It's like a quiz, but it's just homework problems, and then also 4.2. So that's another thing that I didn't see a lot of you turn in. It's completion. If you did it, I gave you full points, right? It's practice on these topics, right? If you completed that assignment, I go into my AP and say like, oh, like Maggie did this assignment, full points. It's just you need to do it. But even if you get them all wrong, I told you to look at the answers. Did the answers post right after you submit it? That's what I wanted you to do. Huh? After you-
go to the result.
Okay, yeah. I don't know how the student view looked. So after you take it, you go to a results tab.
It might take a few minutes for it to load.
Okay. It should be really soon after you submit it. It'll grade it automatically, and then there's that. Right? But the point of that is, you take it, you're like, oh crap, I got 50%. But look at the ones you missed and be like, oh, this was the right answer. Why was it? Oh, I did my math wrong, or I used the wrong equation. Don't just say, oh, got 50%, move on with my life. Practice from that. Like, what did you miss? What were you not doing right? Oh, I missed the kinetic energy equation ones because I forgot it was 1/2 mv squared. That's really valuable for you to learn, right? So that's why I just made it completion. Get it done, do some practice, but then learn from your practice, right?
Those questions were on Khan Academy though.
What's that?
No,
They were on the ones I was talking about.
Oh,
That I didn't understand.
on Khan Academy? Okay.
The rest of the Khan Academy stuff was fine.
Okay.
I didn't understand those questions.
just one of them, or?
Well, the first one, and I could move on from there.
Okay, gotcha. Yeah, again, sorry that I was stuck at home. Yeah, it's been weird. Maggie, what's up?
My computer just got wiped and they changed my password.
And you don't know it?
Try 1, 2, 3, 4, 5.
No, because I saw him typing in something.
Did
I was
they,
thinking, man, that looks longer than my password.
did they tell you, or
No. He said, okay, here you go.
you want to run down and ask him quick so you can open it up? It's up to you. You can if you wanted to. I didn't have a super solid plan.
Okay, that's reassuring.
Because if you want
Does
us
anyone
to
have
do
a super
something on
solid
the
plan
computer
at
as
all this
well.
year?
I have some videos that I'm going to show as a class, and then I had a lot of work time to do another homework set that would be on IP. At that point, you could head down, but maybe wait in a sec. I'm trying to think of. Okay. Any other questions about any of the topics? Right? The first main topic for this unit was systems. Right? Defining a system is important. If I look at a ball in the air and the Earth's surface, and the Earth, that system, I would have to talk about relative potential energy. So I would have to say, how far is it off the ground of the Earth? If I don't include the Earth as my system, I don't really have potential energy because there's no reference point. So that's important. You guys know, again, open, closed, and isolated system. Andre, can you put your phone away, please? Sierra, could you put that away, please? I need you guys to be with me. These last 2 days I've been working overtime trying to get all of my classes back on pace because it was hard to do quarantine. I get it, me not being here, but I want to get us back on track because we don't have the opportunity to fall behind. That May 5th, I'm pretty sure it's May 5th for our AP test, it will not care what we got going on in our lives. That test is on that date. So we kind of have that deadline we got to go for. The second kind of topic of the unit was about energy and mechanical energy, your total system energy. What were the 3 types of energy we talked about? We've been talking about them already. Kinetic energy. Potential? No? What was the other big equation? There's another form of potential energy. If I squish something, it stores energy. Nobody? Spring. Thank you. Spring potential energy.
Spring potential energy.
Yes. Good. All right. Those were 3 big topics. Kinetic. It's a bad name, but I always called it just potential. And then spring. This is U sub S, U sub G, and then K. Right? Should look familiar. What is the equation for kinetic energy? This is something that you should learn, and so it should be on the top of your head. Because we'll do energy, you'll see this over and over and over in energy. 1/2 mv squared. 1/2 times the mass times the velocity squared. What are the units for kinetic energy? No, like units. Not the abbreviation. Is it in watts? Is it in pounds? Joules. Joules is how we measure all energy, at least in chemistry, or not chemistry, science class. Joules. A joule is a kilogram meter squared per second squared. You guys should see that just from the equation. Well, mass is always kilograms. Velocity is meter per second. Meter per second squared is meter squared over second squared. So a kilogram meter squared over second squared is a joule. All right, how about gravitational potential energy? What was the equation?
U sub G equals M times G times H.
Bingo. Mass times the acceleration due to gravity, aka the strength of the gravitational field, and then the height off the ground. What units is MGH? Joules. Same exact unit. All forms of energy are measured in joules. How about the last one? The spring potential energy. You guys remember this one? This is when you compress a spring, you're storing energy. What things affect how much energy you store?
1/2 kx squared.
Bingo. 1/2 kx squared. What is K? Hi there.
Hi, how's it going?
Good. Need somebody?
Maggie?
Just for a moment, or?
Yeah, we may head over to Mr. Morninger's
Okay.
fix her computer. If
Oh.
that's okay.
Gotcha.
Is that okay?
Yes.
Okay.
Yep. Right? What is the K? What? No. That's capital K. We got little k. We've seen this before.
Is it spring constant?
Bingo!
Yes.
Spring constant. What does the spring constant mean in layman's terms? What's the spring constant tell you?
The thickness of the spring? Or
Kind of.
The springiness, the
Yeah.
flexibility.
Yeah, the springiness, flexibility,
Elasticity.
elasticity. It's the best word is the stiffness, right? If I have a huge K value, that's the kind of spring that you put on a vehicle. The suspension, they're so strong, right? You have to use a ton of force to move that spring. It's stiff, strong. If I have a really low K value, you could apply hardly any force and it'll move, right? That's the stiffness. If I have a larger stiffness, am I going to be storing more or less energy in that spring? Think about, is it easy to compress a big spring?
No.
No, you got to put a lot of work into it, don't you? So a stiffer spring stores more energy. Look at it mathematically. If this number goes bigger, this number goes bigger, aka more energy. What's the X mean? Be careful with this. A lot of students get mixed up. What does the X variable mean? So in order to put energy into a spring, I got to push on it, don't I? If I push on it and nothing happens, am I storing any energy? No. Well, what happens when it gets smaller? Then I store energy. The spring moved, didn't it? This X is the displacement of the spring. Be careful. It's not how far you moved the spring necessarily. It's how far this spring is moved from its resting position. A spring is, if you leave a spring on the table, it's going to be a certain length. This X variable is the distance that changes from that resting point. That resting point is, 0. There's no energy if the spring is sitting on your table, right? That's your natural resting point, right? But then squeeze that spring. Do you see how it compressed? The displacement would be how much you move it from rest to kind of your squished position, so to speak. And then the stiffness of the spring is a characteristic of the spring. It's like a fundamental property of that spring. What's the units for spring energy? Shouldn't be a hesitation.
Joules.
Joules, good. It's energy, joules. Those are 3 types of energy that we talked about. What is mechanical energy? Do you remember that term? It should ring a bell. We did this. This was 4.2. It doesn't, well, I guess it technically has an equation, but it's actually already listed up here. How about this? What's the total mechanical energy mean? Use our skateboard example. The skate park. The total mechanical energy was 1,000 joules. At any point in time, these energy types always added up to 1,000. So what would that mean the total mechanical energy is? If these all add up to equal the total mechanical energy, what's the total mechanical energy? It's easier than you think it is. Come on. We gotta know this. The total mechanical energy,
It's fixed.
did you get it?
Yeah.
Did they just have to get you the password?
He said it was the same password, but he ended up putting an S at the end of it.
Oh, that's why it didn't work.
Yeah.
Maggie, dude, help us out. What is total mechanical energy? Remember what mechanical energy was?
Like work? Like power?
No, not quite. We just talked about the types of energy.
It's not the rotation thing, is it?
No?
No.
You guys are, it's so obvious, but I'm not going to give it to you. Pull out your notes,
Yep, that's what we do.
right? Like, we have to know this. Might have been a long weekend, I get that. The total mechanical energy is related to those 3 things. Think about the word total. You guys are killing me. Nobody recorded that? The videos, they did it multiple times.
Man, my memory's gone. It has like the ability of a goldfish.
This moment in time, there's evidence that supports that claim.
Oh, I know. I take a foreign language. Try having a bad memory there.
Oh, you guys are killing me. Total mechanical energy is the total energy in the system. This plus this plus this. Does that ring any bells?
Makes sense.
It needs to ring a bell. We have to know this. That was in the 4.2 videos. Right?
Mm-hmm.
Work and mechanical energy. That was all about 4.2.
Confirm that, right?
That was like pulling teeth. Let me go to your Google Classroom, and I want to look at, because a lot of days I tried to help you and post a, like the key concepts. It was on, Monday. If you look at the post, Monday 11/9. Total mechanical energy depends on the boundaries. It equals K plus UG plus UE, which is elastic. It's the same as a spring. You just add them up. That total mechanical energy is how you describe your system. That's why you were telling me the skating example. You had a bunch of potential energy at the top. So potential energy plus no kinetic plus no spring equals the total mechanical energy. And then you told me when I get to the bottom of the ramp, I don't have any potential energy anymore. I still have no spring, but I have a bunch of kinetic. Well, guess what? The value of that kinetic energy at that point in time is equal to the potential energy at the top of the ramp. Why? Because it's a closed system. Energy wasn't going in or out. Energy was conserved. Remember? Law of conservation of energy? If no work is done, no outside forces affecting your system, how could the energy possibly change? Well, it just switches inside the system. All that potential energy pushes you down the ramp and gives you speed. When you run out, you have maximum kinetic energy, which shoves you up the ramp, but then you run out, you got all the potential energy now. Well, the potential energy pushes you back down, and the cycle goes back and forth. However, at any moment in time, if you add up all the sources of energy in a closed system, it will always be the same at any moment in time. Makes sense. There's no way energy is leaking out of the system. There's no force acting on the system to affect it or change it. It's by itself. Sure, you're changing the types as you go up and down, but the total mechanical energy is conserved. That's that law of conservation of energy of a system. Now, I want to transition to today. I'm going to play some of the videos, and this will be nice because then I can, after we do a video, if you guys are like, Mr. H, I didn't get anything that was said, I can be right there to okay, this is what they were talking about, or if you have a minor question, I can answer that. So, what I'm going to do is go into Classroom. I got to get this up and running. Oh, please don't. I would be devastated. Okay, good. So we are on 6, 7, and 8 is what I want to watch today with you guys. I'm going to assign them. You don't need to do it. But just for me to keep track. These are the last videos or topics for this unit. Right? Oh. What you left off with was watching 3, 4, 5 for topic 4.3. Now we're going to do 6, 7, 8. Again, these videos are really nice. Conservation of energy, the work energy principle. This is where we're going to say, what happens if a force does act on a system? Does it change the energy in that system? The answer is yes. And if you apply a force on something over a certain distance, what physics concept have you just done? Force times distance. This is the very beginning of the unit. Work. Should ring a bell. Work is FD cosine theta. When you apply a force over a distance, you're creating energy. You're putting energy into something. You're doing work. Energy is the ability to do work. If you have energy, you can do work. And if you do work, you're transferring energy to something. That's what this video is going to be about, is connecting energy and work together. The other thing, I got to get the speakers. So I'm going to play this and then see what questions you have. Crank it. It's like Michael Scott at the Glee viewing party.
Crank it up to 11.
Or we can crank it. I love how he says that. Okay, let me get the sound switched. Such a pain. Oh, it's gonna be loud.
AP Physics 1. As always, my name is Defending.
Do you want me to speed it up a bit?
I'm coming to you today from Boston, Massachusetts. So our goal for today is to discuss a problem.
Is that
it's
too
actually a
fast?
response question. So we're going to be
Good?
about
Okay.
the work activity here.
We'll save some time.
I have a question for you. So a spring is compressed by a distance of x.
Please be taking
Thereby
notes and
force
working
and
along with
elasticity
this.
of US
It will be more
So what I want
beneficial
to
to
think about
you.
is how much would the
rather than
energy
just
of
listening.
that spring, how much would it change if instead of compressing it to a distance of x, I compressed it to a distance of 2x? So take a moment to think about this. Pause the video if you need to, have an answer, and we will read it.
Okay, so again, that question. Remember spring potential energy. I'll remind you, U sub S, or sometimes it's also U sub E for elastic. Same thing. Does anybody remember the equation for spring potential energy? 1/2 kx squared. That equation will help you answer this. The question is, you compress it by a distance x, and you get a certain amount of spring potential energy. What happens if you double the distance that you compress it? How does that change energy? Does it double the energy? Does it quadruple the energy? Does it half the energy? You gotta look. Check your equation. Be careful, it's not quite as straightforward as you might initially think. Rely on your equation to tell you how the energy would change if you change the distance.
What's the video?
Work energy theorem. So conservation of energy and the work energy principle, they call it. Does anybody have a guess of kind of the answer? I heard of some of you guys say it'll double the energy. Any other thoughts? It's okay, I want to play it and have her.
So this is the problem, the FRQ problem. Okay. So it says, actually, I'm just going to have you pause and read it yourself. I don't want to read it to you. Okay, so hopefully you have paused and you've read it. So here,
I guess we'll take a second. Block's initially at position 0, right here. In contact with an uncompressed spring at position 0. The spring is it's just sitting on a table. There's no energy in it, it's just a spring lying there, touching the block at point 0. The block is pushed back, there's no friction. Friction isn't doing anything. It's not adding energy, it's not taking energy away. So it gets compressed from 0 and squished back to a negative d distance. The delta x is d, right? From here to here, that displacement is d. Then you're releasing the block. The spring is going to push that block forward. Then it hits friction. This half of the track has friction. And it goes all the way to 3d, a distance of 3d away from that. You have a coefficient of friction mu, and that's the scenario. So then she's gonna walk
the idea
through
of the problem.
and explain
so
this
you
problem.
have this spring, right, and you have a block on it, and this 0 point is the equilibrium position, right? This is the equilibrium position of the spring, but we compress it to by a distance of d, right, to this position negative d, and then release it. And then the block goes flying, and it eventually stops at 3d. Another thing that's important to note is that this first part from negative d to 0 has no friction. However, when we get back to the 0 point, this surface does have friction in it. And it's a constant coefficient of friction of just me the whole time. So the first question, the first part of the question is, you're being asked to sketch the kinetic energy versus distance and the potential energy of the spring system versus distance from negative d all the way to 3d. So where to begin? This is a little overwhelming, doesn't it? So the first thing we have to ask ourselves is, what's in our system? Okay, is energy conserved? And is there work being done by an outside force? So let's see if we can address those questions first. So what's in our system? Well, the block, the earth, and the spring. Those are the things in our system. Is energy conserved? Yes and no, right? In this first part, there's no friction, right? So there's nothing dissipating the energy. However, when it gets to 0 all the way to 3D, the reason why it eventually comes to a stop is because friction is doing work on our system. So energy is only conserved for that first part, and there is work being done by friction from 0 all the way to 3D. So let's get back to our trusty LOL diagrams. Hopefully you've been finding them helpful. You should use them. No one really ever asks you to use them, like on the AP exam or in school, but they're helpful for visualizing what's going on, so you can always draw them yourselves for your own purposes. Okay, so we're going to first decide what's in our system. Like I said earlier, it's the box, the spring, and the earth. All right, we're going to use our conservation of energy statement. So I want you to notice that we're only dealing with this stretch from negative d to 0, because that's the only part of it where energy is conserved. So this energy conservation statement, it is simply for just this part. So I'm going to label where my initial is, which is at negative d, and my final is at 0. Okay, so at the point negative d, we have the spring potential energy, right? And then after it's released, all of that spring potential energy has been converted into kinetic energy for the block. So this is what my LL diagram would look like, right? The total energy remains the same all through. Initially, it's in the form of the spring potential energy, and at the end, it's in the form of kinetic energy. So how will I show that? So that means I need to show that at negative d, I have a maximum amount of spring potential energy, right? And at 0, I have no more spring potential energy left. However, at negative d, I have no kinetic energy yet, but by the time it gets to 0, I have full kinetic energy. Okay, so I know the general idea, but how do I know the shape? Do I do a straight line? Do I curve the line? That's what we need to decide right now. Okay, so we're going to go back to that energy statement, and then we're going to plug in the equations. Right, so this is the equation for spring potential energy. It's 1/2 kx squared. In this case, our x is the distance d. Right, that's what it's being compressed. Right, and that's what's equal to our final kinetic energy. So from this, we can see that the initial spring potential energy is proportional to a square of the displacement. Right, so because of this square that is in this equation. So that means that the shape of our graph cannot be straight. It needs to be a quadratic relationship, right? So we get something like that. Okay, forgive my curves. You already know how I draw. All right. What about the kinetic energy graph? What should that look like? Well, the kinetic energy is proportional to the spring potential energy, right? So if the spring potential energy is proportional to a square of the distance, that means the kinetic energy also has to be proportional to a square of the distance. However, the kinetic energy, instead of decreasing from negative d to 0, it's increasing from negative d to 0 at an exponential rate. So we get a curve that looks like that. So that's the first part. We cannot figure out what's going on in the second part using the state system, because this is all about conservation of energy, right? And we just said that energy is not, in fact, conserved from 0 to 3D, so we need a different way to approach that part. So in the last part, we figured out what the graph looked like from negative d to 0, okay? But we yet to figure out what's going on from 0 to 3D. All right, so we said that for that part, there's actually work being done. In this case, the work is being done by the force of gravity. The force of friction. So the force of friction times whatever distance it acts over is the change in energy. And in this case, the change in kinetic energy, because we're talking about the block, right? Okay, so these are 2 points, right, at 0, which is where the spring is at equilibrium and the block begins to move, all the way to 3D, which is where the block comes to a rest after going through the path that has friction on it. So what types of energy do we have initially? We have kinetic energy, right, and that is our total mechanical energy. But what types of energy do we have at 3D? 0. We have no energy, right? It's come to a stop, right? There's nothing else happening. It's on the ground. So there's no gravitational potential energy, right? It's no longer moving, so there's no kinetic energy, so there's no energy left. where did our energy go? So remember, like we have to account for all these blocks. So we just can't have our blocks disappear. We need to figure out where it went. And the blocks where our energy blocks were taken out of the system by the force of friction, right? It did negative work on our system. So previously we figured out what happened with the first part of the graph. Now it's time to figure out what's happening with the second part. Well, for the spring potential energy, it's easy. The spring is no longer compressed. So from 0 to 3D, nothing's happening with the spring. The energy is still 0. But from 0 to 3D for the block, how do I figure out what to do with that shape? Well, for my work equals change in energy equation, you can see that the distance that it's traveled is directly proportional to the change in kinetic energy. So this is a linear relationship, right? So as the distance with each additional stretch that it travels through, the amount of energy that it has goes down at a constant rate. So I'm going to have you pause again and read this part. This is part B of the problem. So pause the video, read this part. Okay, so in essence,
did that first part of the video make sense? Right? When you compress the spring and let it go, it goes back to its starting point. It's frictionless. There's nothing, no force is acting on the system, so your energy stays the same. You compress it and it makes potential energy. Then you let the system go. Well, all that potential energy is released and turned into kinetic, and it's conserved. Did you notice that once it hits the rough part of the track, you no longer conserve energy? Did you see that the energy left the system? Right? The energy still exists in the universe. It basically, friction turns energy into heat, and then the heat escapes. But in our system, we lost energy. Do you guys get why? What took the energy out of our system and slowed the block down? The friction. Good. How did it do that? What's the other physics word we've been talking about?
Oh, I always mix it up.
She said it. It's a simple word. What did the friction do on the system to pull energy out? 4-letter word, starts with a W. Work. Work is applying a force over a distance. Friction has a force, doesn't it? Did it act over a certain distance? You bet it did. What direction was the force pointed? The block is going this way. Friction points this way. It always opposes your motion. Well, if it's opposing my motion, it's doing the opposite of my kinetic energy. It's sucking out the energy until it eventually runs out of energy and stops. Now I have no energy in the system. That's really important to see. That's that work energy principle. The work done on a system can either add energy into the system or it can take energy out. Right? So this question is, okay, the spring is compressed twice as much. This was that thought question at the beginning of class, or the video. Now you pull it back to 2D. And then you got to predict, is the final position going to be twice as far, 6D, or is it going to be something different? Actually, in this case, the student assumes it's twice the distance. We got to figure out if their assumption is correct and why.
Student is asked to predict what's going to happen if we double the compression distance. So instead of compressing it a distance of d, what if we kept compressing? So now we compress the spring even more, all right? And the student thinks that the block will have more energy, right? Because you're compressing it more. And the student is also predicting that instead of stopping at 3D, the block is now going to stop at 6D. So we need to figure out what parts of their statement is correct and what parts are not correct. So I'm going to highlight the correct part in green and the incorrect part in red. So this part of the statement is correct. That's true, right? If you compress the spring more, it's going to be able to, it's going to store more energy, right? So when the block leaves the spring, it's going to leave with a higher amount of kinetic energy. That's true. I don't know about this though. Like we don't know for sure if it's 6D. So why don't we try to figure that out? And then we can figure out if we want to highlight this part of the statement green or red. Okay. So let's figure that out. Oh, actually, before we figure that out, let's explain why the first part is correct. So let's put it into words. So we're going to use our conservation of energy statement, right, and just say that whatever the initial energy starts with is in the form of spring potential energy is going to be the final total amount of energy in the form of kinetic energy. Okay, so energy is conserved from initial compression to the release. So if you compress more, the system is going to store more energy. Therefore, there's going to be more kinetic energy when the block is released. Okay, this is the part we're not so sure about. Is x equals 6d, is that correct or incorrect? Well, let's figure it out. We have all the tools we need. So we're going to start with our work equals change in energy statement, right? And we know that the force of friction times the distance that it acts over is the change in kinetic energy. This change in kinetic energy is equal to the initial spring potential energy. So we can plug in the equation for that, which is half kx squared. We're going to use a factor of change method. I bet you missed it. So let's use a factor of change method. Remember, for the factor of change, you plug in a 1 for everything that does not change, and you plug in whatever the factor of change is for whatever does change. So in this case, we're trying to figure out the factor of change of D, right? The force does not change, so we plug in a 1. Half is still half, so we plug in a 1, right? The spring constant does not change, so we plug in a 1. But for the compression distance, it changes by a factor of 2, so we plug in a 2, and we get that the factor of change, so the distance is not 4, the factor of change of the distance that the block travels is 4. And our distance that it traveled before was 3d, and we multiply that by 4, we get that now it travels 12d. So is the student correct? No, they said 6d, so it actually travels twice as much as they predicted. Okay, so let's see if we can put this mathematical explanation into words. So the energy that's stored in the spring is, transferred to the box, and that is not proportional. It's proportional to the square of the compression distance, right? So it's not a linear relationship. It's proportional to the square of the compression distance. So that means that the work done also that it has to be proportional to the square of the compression distance, because the work done is proportional to the energy that was stored in the spring. Okay, so what that means is that if you double the distance, right, you need to change, the distance is going to change by a square of that. So that's how we got to that 12d. So this is the explanation that we did in the equation form. This is it in the words form. Okay, so what should you take away from this video? You take away that whatever the work is done, that is done in the system is equal to the change in.
You want to take notes? This is what I would take notes
in
over.
the system consists of just one object. Remember, one object by itself can only have kinetic energy, so that means the work done on that object is equal to the change in kinetic energy of that object. And we review factor of change method again, so that hopefully you can get more comfortable with it. Thank you for learning with me today, and I hope to see you in the next video.
So in case you missed that, right? The work energy theorem. If you do work on a system, you're changing the kinetic energy. In this case, we only had kinetic energy. Right? We did negative work on that system. Negative work means you remove energy. That's why the block stopped. You pulled out all the kinetic energy via friction by doing work and sucked out all the energy of the system until it was at a standstill and there's no more energy in your system. That's that work energy theorem. It's basically just comparing, okay, if you watch the energy of a system, but somehow work is being done, the total energy changes. If we had done positive work on our system, what would have happened to the total energy of the system? If I had done positive work on my system, would my total energy go up, go down, or stay the same? Brody's got it. What are your other thoughts? Up. Good, good. Positive work means you're putting energy into the system. So the total energy goes up. This situation was negative work. The force was acting opposite the motion, so you get a negative work value. Well, if you have negative work, you pull energy out of the system. We saw that it came to a standstill. That means no energy was left over. How did it leave the system? Left the system via work done by friction. That's the work energy principle. Again, energy is defined as the ability to do work. Work and energy are synonymous. They're the same. If I do work on a system, I'm changing the energy somehow. What questions do you have about that just general concept of the work energy theorem? Does that make sense? Our energy wasn't really conserved in the system because work was happening. It changed the energy of our system. I haven't looked at these videos since I assigned them or planned them. Okay, question. Do you want me to play the video? These next two videos are about calculating the work that gravity does. Gravity does work on a system, or it can. Do you want me to watch these together and see if you have questions, or do you want me to, your assignment is to practice 4.3 topics. So what we've been doing this class and then last class. Or do you want me to turn you loose on those questions, like the homework questions? I can help you in class, and you guys watch these videos as homework or on your own. What?
I vote the same.
Second one?
Yes.
Okay, so I would agree. I think that would be more helpful. Why can't I get out of that? There. So you guys should see. Oh, I didn't assign it. Dang it. Ugh, 26 of them.
Uh-huh.
26 questions.
Yeah, I don't want that many. Do you want me to do half of these? Just like maybe 10? Do you want me to pick 10 of them? Okay. Yeah. Sorry, I thought I had made this. Yeah, I didn't. Think through which. All right, there. Assign that to both classes. Okay, so I should have assigned it to myAP. Again, the homework that I want you to do is look at 4.3. I gave problems to kind of practice the skills that we learned in 4.3. These are from videos from the last class, which you should have watched, as well as today. It's conservation of energy and then the work energy principle. There might be some power questions. Do you guys remember what power is? Anybody remember what power is? Work and power were very similar. You guys remember that? Power is work over time. If I do 10 joules of work in 1 second, or 10 joules of work in 10 seconds, who is more powerful? Who does it faster? In 1 second or 10 seconds? 1 second. 10 divided by 1 is 1 joule second, or 1 watt. You're good. What was that from?
I don't know. I just logged on to AP Classroom.
Oh, I don't know.
I don't know what that was.
10 joules in 10 seconds is 1 joule per second, or 1 watt. 10 watts is more powerful than 1 watt. Right? If you have horsepower, we rate cars by horsepower. The more powerful an engine, the more it could do in a certain amount of time. That's why you need a lot of power in a car to accelerate quickly. The work is the same, but how quickly can you do that work? How quickly can you go a quarter mile? The work's the same, but who can do it faster? That's what power is. So that's another side topic. So I want you guys to, again, spend the rest of class working on these problems. Do them on a piece of paper. Actually solve them out. Record what you did. Because, again, when you get the results, you can be like, oh, crap, I missed that first one. What did I do wrong? Oh, I wrote the wrong equation. Or I didn't even use the right equation in the first place. Right? But I want to be here. If you have questions, like holler at me, and I want to come help you right now. Right? And then I just have you do video 7 and 8. Those are the last ones. Just watch in your own time. Make sure to take notes on them. And then that'll wrap up. And then basically we will review next class. Get you set up to, you need to be reviewing over the weekend, and we'll test Monday. Alright? So that's the game plan. Any other big questions? Okay. Again, I'm going to pause this, and I'll be here to answer any questions you have on those